So this lecture is going to be given in English for everyone. I know you might be tired at the end of the day, but I'll try to give it as interesting as possible. So if you want to use your smartphones, this is the time. You can scan the barcode on the screen. So I'll introduce myself shortly. My name is Nir Diamant. I'm an AI consultant, and I run a community, a Gen AI community. We have a Discord. I am the maintainer of world top open source tutorials. You can find all of them in my website with over 17K stars, and I run also a newsletter that I write about those tutorials and other Gen AI stuff. So you can find it there. And now it's the time to put your cell phones back in your pockets. So let's start. This lecture today is going to be about controllable agent for complex RAG tasks, and I'm gonna describe what it is. So the agenda, sorry if it's blinding you. The agenda is first, what is RAG? Then we're gonna talk about what are agents, why we should control them. Then how can we build a controllable RAG agent, and a short demo at the end. So the use case that I'm going to talk about is the first book of Harry Potter. We're going to questions and answers over the first book of Harry Potter, and the reason that I chose this one, usually I like to ask the people why should I choose this Harry Potter book as the use case. But in this case, because we're a big audience, I'm going to tell you that Harry Potter is a book. It contains a complicated plot, and the questions that you can ask about this book could be complex as well and non-trivial for RAG. All right, so in a sentence, for people who are not familiar with the term RAG, RAG is an acronym for retrieval-augmented generation. And it's a method that helps AI language models to generate text-based on external information data sources. How it works. So we're taking our Harry Potter book and we're chunking it. We can chunk it into sentences, pages, whatever granularity that you choose. Then once we have those chunks, we take them and we embed them. We operate a function that takes those chunks into a much lower dimensional space. I'm going to talk about it a bit later. And all of those vectors are going to be stored inside a vector store. Then what happens? The user asks some query. The query is also being transformed the same way into this lower dimensional space and compared with the vectors in the vector store. Then the most similar vectors are retrieved, being fed, decoded first, being fed into the LLM together with our query, and now we have our context with the question or query or whatever, and we can get our answer. Great. Agents. What are agents? So LLM agents are advanced AI systems designed for creating complex tasks that need sequential reasoning. They can think ahead, remember past conversations, and use different tools to adjust their responses based on the situation and style needed. So this graph here shows you, I made this graph, but just to give you the intuition of the trade-off that we have to pay between the level of autonomy the agent has and the amount of control that we have. So the more autonomy the agent has, the less control we have over it. And the trade-off is kind of describe it in this table. So using a regular agent, we have no control over when it uses its tools or in what order. We have no control over the conclusions it derives from using the tools, and it's very hard to trace hallucinations that happen during the process of the agent. And when we're constructing our own workflow, we can define our specific path of how we can tackle the problem as human beings. We have full control over each step, but the trade-off in this case is we have to tailor the solution specifically to our problem. It could be difficult and time-consuming, complicated. We can make mistakes, and so on. So just before I'm going to describe which building blocks we need to create a controllable reg agent, I'm going to talk about the semantic similarity. So the embedding space that stores those vector stores is trained to put words that are semantically similar together, and those who are far away further. So in this case, we have the word king and the word queen. They are they're laid very close in this space, and the word dog, for example, is further. So I give this example to show you a simple reg problem. Sorry. So in a simple reg problem, for example, we have a book, a history book, something with historical events. So a query could be what happened in France on July 14, 1789. And in this case, this history book contains a sentence saying on July 14, 1789, the storming, and so on. In this case, searching the vector store is going to be very easy because we actually have the same phrases, wording, and so on. But what happens if you want to ask a bit more complicated question as how did Harry beat Professor Quirrell? So we were not going to find a sentence in the book saying Harry beat Professor Quirrell by doing this and this and this and this, right? And so for dealing with this, we could create additional vector store containing the book chapter summaries. Also, we can use an LLM to create it. In those summaries, it's more reasonable that we can find the solution for this. Now, if you want to have a much higher precision, so for example, specific quotes from the book. I don't know how many of you read Harry Potter, saw the movies. I guess many of you. There is this very famous quote of Hermione saying, "We could have been killed, or worse, expelled." So if you were going to ask, according to Hermione, what's worse than being killed? I mean, you'll have to have the specific quote from the book, otherwise you cannot solve it using an LLM. So in this case, what we can do, we can create additional vector store composed of all the quotes from the book. So in our case, we have 3 different vector stores: the chunks, the regular chunks, the summaries, and the quotes. So a naive flow engineering for this, to solve this is an agent by LangGraph. And so a naive solution for this could be the beginning. We have our query. We want to retrieve context for this question. And then we want to keep only relevant content out of it. Then we check, is it relevant? The context that we drew from the vector store, is it relevant for the query? If yes, answer. Verify it's not hallucination. And if it's okay, we're done. If it's either not relevant or not useful, we can rewrite the query, going back for another loop, try it again, and continue like this. So, and this is the implementation. Obviously, I'm not going to go over this. It just show you how simple is this just to write in LangGraph. I'm a LangGraph advocate, by the way. And going back. We could have been finishing this lecture at this point, but I want to tackle more sophisticated and complex questions. Sorry. So, for example, if we have the question, how did the protagonist defeat the villain's assistant? This is a very non-trivial question for anyone who hasn't read the book, right? And in order to solve this, we need the following steps. First, identify who is the protagonist of the plot. Then, we want to identify who is the villain. Then, we want to identify who the villain's assistant is. Only then we can search for any kind of confrontations or interactions between the protagonist and the villain, and just at the end, we can deduce the reason that led the protagonist to defeat the assistant. So, in our agent, we may need the following capabilities. First, we need tools. Then, we need reasoning. We need flow of how the agent is going to operate. We need to control this, and we want to verify that what's happening there is actually what we want to happen. We need to know when to stop, and we need to evaluate that all what we've done is actually what we want to be doing. And so, in our case, the agent tools should, it's a suggestion that I've made, so I suggest using retrieval and answering tools, and we could break the previous graph into two different types of subgraphs. First is going to be for retrieval. So we're going to have a tool for retrieving the book quotes. And actually, we are also verifying that we keep only the relevant content. We want to have the same for the summaries of the book, and we want to have for the chunks. So this is, an additional family of the answer tools. In this case, just one answer tool that answers and verifies it's not hallucination. Great. So the components that we need to have in our agent are, first, we need to have a planner. Given a question, we want to have some agent that thinks, what steps do we need to do in order to solve this question? We don't know that these steps are definitely going to solve it, but it's just the beginning point of the agent. We want them to break it down into steps to either retrieve or answer tasks, then use a task handler that is kind of sorting each task to either the retrieving or answering tool. Then we want to have a replan component that during the run of the agent, we want an ongoing component that can think, all right, we've done this and this and this so far, and now we have this information, and what is the plan at this point that we want to build in order to solve the problem? And we have our tools, the retrieve and the answer tool. The flow. So I added additional component to this, which is a question anonymization. And this is to avoid any kind of prior knowledge or biases that the LLM has. For example, ChatGPT, he knows Harry Potter, right? We can actually ask him any question that we want and he will answer. But if we use additional LLM who has other biases, we don't want them to be involved into the process of building the plan. So for this, we can replace every name entity into a variable. So in this case, if we're asking, how did Harry beat Quirrell? So we can replace it into, how did X beat Y? And according to this, we can build our plan. After we've built a general plan for those variables, we can replace them again and get our generic plan based on our own names. So this might be a bit overwhelming, This is the whole solution. So stick with me. I'm going to go over this quick. So first, we start with our query. We want to anonymize the question. We want to build a plan. We want to de-anonymize the plan. And then we want to break down the plan to either retriever answer tools. Then we have the task handler that actually does this and chooses, if it's a retrieve task, then it chooses either one of the retrieve book chunks, the retrieve book quotes, or summaries. Then it filters out all the non-relevant information. Otherwise, if we're going to the answer tool, so we answer some kind of intermediate question, and we're verifying it's not hallucination, and then we get to the replan step. The replan is thinking, all right, we have all the information gathered so far, and we know what are the past steps that we've done so far. All right, can we answer the question? If the answer is no, so we're building a new plan from this point, and we're going for another iteration. If we're good to go, we're saying, all right, give us the final answer. Again, we want to verify it's not hallucination, and we're done. We want to have a stop condition as well. So how can we determine when this process is done? So there are several alternatives. First is one I've shown you before. It's every replan visit, we ask the replan component, all right, are we good to go? Can we finish now or not? And the two other options is first, the second one is keep collecting relevant data until we get some kind of saturation. We don't have any new interesting information added to the old agent. And lastly, we can limit the graph recursion by some kind of predefined number of iterations. For, let's say, after 100 visits on different nodes, we can say, okay, probably it's either we can't get any more interesting information or we cannot answer the question. I mean, I could have asked this agent, based on the first book of Harry Potter, a question about the second book of Harry Potter. And I wanted actually to not make it to answer the right answer, right? So after 500 iterations, I say, okay, you cannot just solve it. You know, to evaluate the model, since it's a RAG problem, we can evaluate it just as other RAG problems. So we can measure the answer correctness to check if it's factually correct. We can measure the faithfulness if the answer is based on the context or hallucinated by the LLM. We can check the answer relevancy, which is actually how relevant the answer is to the specific question that we have asked, and not something near it or including it, and so on. And we can check the similarity between the ground truth answer and our answer. Now, we're supposed to be seeing a demo. How can I run it? No. Some technical guys here. Skip it? All right. So there was an amazing demo that we've just missed. Just saying that the demo is a visualization of the agent, like in an ongoing manner of when it runs, we can see the plan, the current plan of the agent, the previous steps that we've done, and the aggregated context. And we can, I gave a question that is hard to solve. It's what is, I forgot, something difficult. You can find this actually online if you want to see it. And yeah, that's it. If you haven't scanned it before, you can scan it now. And thank you very much.